Okay, so this note is about normal forces. So whatever I'm putting on this note app, please put into your notes. So normal forces. We're going to start with an object on a flat surface. Maybe it's a book or something. So let's take a look at the forces here. Now we're just imagine it's sitting here. Well, gravity is going to pull this book straight down. So we'll call this F sub g. And from your notes, the way you calculate the force due to gravity is mg, right? Because if F equals ma, F equals m, and then the a in this case would be the acceleration due to gravity. So it's still the Newton's second law, F equals ma. It just means that in this case, the a is g for the weight of an object. Okay. Now, if this was the only force acting on the book would be accelerating downward towards the Earth's core. Obviously, it's not doing that. There must be a third law pair to this. And if you think about it, the book pushes down on the table pushes up on the book. And this reaction force is the normal force. So this reaction force is the normal force. It is the opposing force to the weight of the book on the table. It's the table pushing up on the book. Now, we know that the normal force has to be equal to the force of gravity. Why? Because the book is not accelerating upward or downward. So we'll say because the book is not accelerating up or down. So this is an important concept for physics and for this unit, is that if the book is not accelerating, then these forces must be equal. They must be canceling each other out. Or another way to say that is if you add up all the net forces, Fn plus Fg, the net result is 0, which is really just saying the same thing as this, that these two things have to be equal. They just go in opposite directions. Okay. So that takes care of the normal force on a flat surface, that the normal force is equal to gravity. I want to point out something real quickly here, that if you take that same book, and let's put it back on the table, but now let's say that your hand, this is going to be a terrible hand, your hand is pushing down on this thing, right? So in this case, we have the force due to gravity, it's the weight of the book, but you're also pushing down on the book. We'll call this the F push. So if you push down on the book, then think about it logically. The table has to support not only the force of the book downward, right, the weight of the book, but it also has to support against the force of your push. So in this case, the normal force will increase. So the normal force here has to increase in value because the book is not going to accelerate through the table unless you're like the Incredible Hulk or something, just smashing it through. But if you push down on this book, the table is going to push up even harder on you. You know that the table pushes up on you because let's just imagine that you're pushing the book down super hard. It's totally possible that you could break your arm doing that and the only way you could possibly break your arm is if the table was pushing up on you and pushing up on your arm. That's what would cause it to break. So in this case, you can actually push down on the book, and now the normal force has to counter both of these forces. It has to be equal to the force of the push plus the force of gravity. Right? So the normal force does adjust. It can adjust to support whatever forces are opposing it. It could just be, in the case right here, just simply the weight of the book, or it could be down here, the weight of the book plus an additional force that you're putting on it. So those are the normal forces on a flat surface. Let's talk about the normal forces on a ramp. So normal force on a ramp. So let's draw a ramp right here. And I just discovered if you hold this down long enough, it makes a straight line for you. That's kind of cool. And let's put this book on a ramp. So the book's not going to be on a flat table anymore. The book is going to be on a ramp. So let's do that. Oh, cool. Okay. Now let's take a look at the forces acting on the book. Well, gravity always goes straight down, so we're going to still draw gravity going straight down. Hey. And that is still mg. Okay. Now here's where we get into the definition of a normal force, and that comes from the PowerPoint notes. Now the normal force is a supporting force that is perpendicular to the surface plane. And that sounds complicated, but it's really not. Get off there. The normal force for the surface is going to go like this. Perpendicular, right? So if there's a perpendicular, it's a little thing there. So this will be the normal force here. Actually, let me just get that a little lower, that N a little lower here. There we go. So this is the normal force on a plane, or sorry, on a ramp. It's perpendicular to the surface. Now notice right here, and this is super, super important, that Fn can't cancel Fg because they go in different directions. So there's no possible way that Fn is going to be, that this normal force is going to cancel gravity, which is why, again, think about it logically, this is why the object begins to slide down. Because Fn doesn't cancel Fn, so we can say Fn does not equal Fg. Okay, so let's take a look at these force vectors. Again, the arrows really represent vectors. Again, those are from your notes on sections 4.1, 4.2, and 4.3. And we can draw vectors with arrows. Now, it doesn't look like we can make a right triangle with these two force vectors, but we actually can. What we can do is, and I'm going to try to do something clever here with my, we'll see if this works. We can take this force vector, and we, that was too clever. That was far too clever. Let's try it one more time. We could take this force vector, and we can shift it down this way. So I didn't do as much of the force. You know what? I'm just going to, that was a cool little experiment I tried. Let's just do it a different way. This vector we can take and we can redraw it. We can shift the vector, just simply shift it downward, which is what I was trying to show. That we can take it and just move it down like this. That's my arrow. You can't, it's a little messy in there, but that's my arrow pointing up. So we haven't changed the direction of the normal force. It's still perpendicular. We haven't changed the magnitude or the amount of the normal force. It's still the same size vector. We just shifted it downward so that we can see how the normal force interacts with the force of gravity, or how it sort of compares. So now if you think about it here, we have these two forces. And this third side of the triangle comes right here. And it points, notice how it points directly parallel to this vector. This is the reason why the box will begin to slide down the ramp, is because there is a force directed down the ramp. This force, it looks like two little hash marks. And this is very important. This is called force parallel, or parallel force. It doesn't really matter. Oftentimes we'll just call it the parallel force. But it's parallel to the surface plane. So parallel, so here's the surface plane. I'm sort of drawing it in red right here. This force is parallel to it. And that's why it's called the parallel force, or force parallel. Remember that forces can only cause accelerations in the direction that they point. So the only reason this object begins to slide this way down the ramp is because there is a force directed that way down the ramp. And that force is called the force parallel, and it is the part of gravity that is not canceled by the normal force. Remember that earlier the normal force canceled the force of gravity because they pointed in literally just opposite directions with equal strength, and so this object did not move at all. There was no acceleration here. In this case, the normal force, which was pointed this way, it can't possibly cancel out all of gravity because they don't point in the same direction. There's going to be some leftover force. Turns out that leftover force is pointed directly down the ramp, which is why this object starts to accelerate down the ramp. The force parallel is that leftover part, or it's the part of gravity that's not canceled by the normal force. And you can just imagine, you can imagine that the steeper the ramp, the more off angle those two forces are, which means there's even less gravity that's being canceled, which is why the steeper the ramp, the faster it accelerates downward. Because the steeper the ramp, the less gravity is canceled by this supporting force. So that's just sort of an interesting little side point. And conversely, the shallower or the smaller the ramp, you can see that now the normal force is pretty close to canceling out all of gravity, which is why this thing barely accelerates downward at all. All right, so those are the normal forces on a ramp. The last thing I want to do is talk about the equations right here. I'm going to do this in green. So if this ramp right here has an angle of theta, there's a little bit of geometry you can do to prove that this angle right here has to be the same theta. I'm not going to prove it right now. It's an interesting little side. I think I offered it for extra credit last trimester. Maybe I'll do that again. If you like geometry proofs, it's not a hard one, but it's kind of fun to do. But anyways, this triangle, the ramp itself, this whole ramp itself is a similar triangle to the force triangle on the inside that I'm doing in green here. So now there's going to be some equations. F sub g, if you think about if this triangle is a right triangle, I'm talking about in the inside now, that means that this is the hypotenuse, right? Because that's this side right there. So now the normal force, we got to figure out an equation. If theta right here, the normal force is the adjacent side to this angle. So the normal force, I have to do this tiny, I think. Fn has to be equal to mg cos theta, right? Because the normal sine or cos theta is adjacent over hypotenuse, and if you do a little bit of algebra, you just solve for Fn. It's mg cos theta. F parallel is the opposite side. So sine theta is equal to F parallel over mg. You can rearrange that and you get mg sine theta. So this is the major takeaway. These three equations. In fact, what I'm going to do is, you know what, why not? Let's just do another quick one. So the main takeaway here is this, that force of gravity is mg. The normal force on a ramp is going to be mg cos theta. And the parallel force, that's the force that points it down the ramp, is going to be mg sine theta. And again, I'm not going to re-teach this whole thing, but these are the directions of those forces. And maybe this is a cool slide for you to sort of commit to memory. Right, so that shows now how what these forces, where these forces point, and what their equations are. All right, so that is the notes on the normal force and how to calculate the normal force on a flat surface and also on a ramp.